be recording, guys. Somebody remind me, please. So I have to do this for vertical, and I notice here that the bottom part doesn't factor. So I have to just set it the way it is. So move the 8 over, and then take the square root. The key is to remember, as Luke said, plus or minus. Okay, it's got to be plus or minus. Now I can simplify that to 2 root 2, right? That simplifies, but I don't really care at this point. You know what I'm saying? You should really know its value as a decimal. What's root 8 approximately? Why do I care about the decimal value, by the way? Why do I care about the decimal value?
Oh, so like you can approximate it like for the coordinates.
Yeah, on the graph, you have to graph a decimal. It's not, what is root 8, right?
Say it's like probably 2.9.
Yeah, it's right near 3. Because root 9 is 3 and root 4 is 2. You should be able to approximate stuff like this. So this is around 3. Okay, around plus or minus 3. It's not, but it's around there. It's fine. Who cares? So on the graph, we know already that will look like that. So you know what we should do? If I'm doing this on the test, I'm probably showing this on my graph as I go through. So here's the horizontal. It's hard to see the horizontal. It's in pink. The vertical's in blue. So I've got my asymptotes drawn. Now I need, is there a hole? Right? Why not? What's the key indicator when there's no hole? How do you know there's no hole in the graph? You need a repeated factor. Very good. And by default, if they don't factor, you can't have a repeated factor, right? So nothing's going to cancel here. No hole involved. Let's do one with a hole after this, though, to show that. What do I go to next? What do I go to next? Bridge after holes? Intercepts. How do I always find the intercepts?
For the y-intercept, it's that x equals 0. For the x-intercept, it's y equals 0.
Yeah, you go back to what you learned in like the second day of math, right? You set the opposing intercepts equal to 0, or coordinates equal to 0. So if we set y equal to 0, x equal to 0, it's easy. It's 4 over negative 8. That's negative 1/2. That's why the coordinate needs to be written this way. I'm telling you now. I didn't take up points in the quiz, you notice, right? If it's not written as a coordinate, it's not right. Because if I write y equals negative 1/2, that's a horizontal asymptote. Y equals some number is a linear function that's horizontal. That's defining a horizontal asymptote in this context. So this needs to be written this way. Is that clear what I'm saying? The vertical asymptote needs to be written as x equals. Because it's an actual equation of a vertical line. This is not a coordinate. X-intercepts are coordinates. On the quiz, I didn't take off points. On the test, I will. Okay, so what are the x-intercepts here? What are the x-intercepts? What do we got? Come on, what do we got? Let's go. Inspection. What are they? It's so easy. What are they? Come on, guys. No one knows, really? Ashley, you don't know this one? What are the x-intercepts?
Positive, radical 8, 0, and...
Those are the vertical asymptotes. What are the x-intercepts? Okay. I didn't mean to put you on the spot. Sorry, I thought you knew because you were looking. Thank you, guys. It does. Every time I give a question doesn't mean there's actually an answer. Please, right? Use your gut. Did a lot of you think there are none here, right? You're right. There are none. There are no x-intercepts. Why not? Why not? Come on. Think. There's no x in the numerator, first of all. That's one thing, right away. So you set the numerator equal to 0. If 4 equals 0, that's a contradiction. So there's no solutions to 4 equals 0. Remember, no solution? Why else? This is not always true the next part, but it might help you to understand too.
Generally, when you have the y equals 0 they'll just like curve it off.
Yeah. A lot of the time, very good, Tristan, very good. A lot of the time when you have a horizontal asymptote right here, it has like a curl, right? We've done this? Or a curl, and maybe it goes through here and you have one x-intercept. We did that one. But a lot of the time, when you have y equals 0 as a horizontal asymptote, you don't have x-intercepts. Not always. You can cross a horizontal. We'll talk about that. But usually you don't. Okay? Usually you don't. So that's all we've got for this. There are no x-intercepts. So I can plot my y-intercept. It's right here. And I'll tell you already, I know what this graph is going to look like. How do I know what this is going to look like without even putting points? I'm not even picking tables yet. I know it's not going to cross the x-axis, right? So you see the one coordinate I've got?
It's going to be symmetrical because the x equals also another minus
Yeah, take a look, please. Earlier in this chapter, we talked about odd and even functions, and I said this is a pre-calculus thing. This means that this is an even function, so there will be symmetry about the y-axis. If this was x cubed or x to the fifth or any of those, this wouldn't be true. Is that clear what I'm saying right now? So I know that whatever occurs here will occur here. Whatever occurs here will occur here. So I'm telling you already that this is probably going to be something like this. It's going to be my guess. Okay, if I don't know though, what do I do? If I don't know, which I usually don't, what's the last part of the acronym? P stands for points. Plug in points. I recommend you plug them into the factor form. Oh man, there's no factor form. Get over it. It's not bad. You can do it. It's just arithmetic. Thank you. Okay, it's just arithmetic. I think it's easier with factor form because what if
just this?
Well, what if you have decimals and it's square now? Is that annoying to square decimals and stuff? All right. Calculator. If you can do it quickly, it's different. So let's go ahead and do this. So here's the question, though, you need to answer. Ready? What points do I choose? That's the key. There's no right or wrong answer. I mean, there is. But there's no right or wrong answer for every single one. They change based on the problem. How do I choose X in a strategical fashion? How do I choose X in a strategical way? Come on, help me out. Come on, people. Choose them near what? What did I say in class? Near the? Which ones? Which asymptotes? Because those are represented by X, aren't they? Aren't these the vertical asymptotes right here? And they say X equals. So choose points near those asymptotes. So choose a point like 3, because it's not the asymptote, but it's close, isn't it? We said that this was around 3. So let's choose 3, and what else? If I choose 3, I should choose. But I'm probably not going to have to because of the fact that this function is what? Symmetrical. So I'm probably going to get the same exact answer. And you know what? I am. Put a 3 in for X. What do you get? 4 over 1. 4. Put a negative 3. You get 4 over 1, which is 4. Okay, because of the symmetry. So you know what? You're going to plot all the negative coordinates, but don't test them all. Use your context of the problem. This is an even function, so there is vertical symmetry involved here. Next, what point? After 3, what should I choose? Come on. I know that this is around 2.9, right? And we chose 3. So maybe go to the next number after 3. Maybe 3.5 or 4. I don't care. Give me a number. Give me a suggestion. Okay, 3.5. Let's do that. And then we'll use negative 3.5. And then maybe 4 and 4. Okay, good. So we've got points to the right. And it looks like they're going to appear here, here, and here. Look at that. Oh, and then we get them over here, here, and here. That's great. I'm done with the points to the right and left, right? Now I need points in the middle. Give me points in the middle. Yeehaw, what do you think I should use? Give me some examples. I know the value when x equals 0 already because I've got the y-intercept, so give me other points. I want to know what this is, yeehaw, and what this is, and what this is, and what this is. So give me some suggestions. Okay, 2 and negative 2, that works. What else? I did 0 already, so maybe 1 or 1.5, so numbers like that. So try 1, and try 1.5, or 1 and negative 1 to start, and then go to the others. But what I'm saying is, there's no right or wrong. The idea here is that we don't know the shape, so get some general points, and then know that they're going to become asymptotic. Asymptotic means the curve gets closer and closer to the vertical asymptote. So once you have a couple points, you know the general trend and what it will look like. So this is the approach we're going to take to graph all these functions. The last part with points chosen, strategically choosing points. Would it make sense for me to choose x equals 20, 19, 18, 17? They're probably all going to be right along the horizontal asymptote. By the time I get out to those values, I'm going to be all the way along the asymptote, and this is what the function looks like. Is that really interesting to me? A function that doesn't want to change height for a while? No. So what I'm doing is explaining to you guys to look at the area of interest in the function. If you use Wolfram over the weekend to study and to practice, you should. Use Wolfram to create some functions if you want. I gave you a lot of practice, by the way. There's a test 12 review on documents and handouts. There's a whole PDF of a PowerPoint on examples. There are a lot of examples. There's a business application of examples you can do to practice. And I listed a bunch of problems to do there. Go to documents and handouts over the weekend. You'll see 3 ways to practice. 3 ways. Okay, so if you don't have a problem set, you got test 12 review, a bunch of examples solved, and then the business applications. All 3 of those documents are under documents and handouts. So over the weekend, when you want to check that you're right, you go to Wolfram, type in the function, or use your calculator, type it in. But what Wolfram does is kind of cool. It zooms in automatically on the area of interest. So if you have vertical asymptotes at 2 and 7, and a horizontal at 6, it'll zoom in on that area and give you all the features in that area. Okay, because that's what's important now. Obviously, the function continues forever in both directions, but we know the end behavior will be getting closer. We'll be getting closer and closer to y equals 0, or the horizontal asymptote. So this graph will tend to go toward it over time. So don't care about that.
Is the test going to be like 30-point test or?
I'm gonna guess it's a Monday's it's an E-day. It's an E-day, so schedules will be a little bit shorter. So 40-minute period, so I'd say 35 points. There's enough to ask you on. So consider the fact that E1, E2, and E3 built this instance, right? So for example, if I said to you, when does a hole occur? Tell me, when does a hole occur in your own words? Or if it was multiple choice, when does a hole occur?
When two, what's like a numerator function, cancel out.
What cancels out? You need math terminology, math things.
Cancel out, make the equation 0, 0.
Very good. When the factors cancel out in the numerator and denominator, or you can interpret it as when you plug in 0 into the function, when you plug in a number into the function and you get 0 over 0, and you get an indeterminate, good word, right? Indeterminate answer, not an undefined answer. When the answer is undefined, say I plug in a 3 and it becomes 7 over 0, it means 3 is a what? It should be instantaneous. If I plug in 5 into the function and I get 0 over 0, it's indeterminate and therefore a whole. When I plug in 3 in the function, though, I get 7 over 0. That is not a whole. What is it? A vertical asymptote. Because the function is undefined at a vertical asymptote. There is no definition to it. It's undefined. Indeterminacy is a form of being undefined, really. Because there is no definition there, right? With a hole, it's not a filled-in circle, okay? But it's 0 over 0, so we use the phrase indeterminate to describe that. Let's do it, and that does have a hole involved, okay? How can I make a function like that? All I got to do is make sure what happens. What happens? Come on.
They have the same factor.
Yeah, so give me the denominator you want to use, Hannah. Give me a binomial denominator.
X plus 5.
All right.
minus
No, just the binomial, x plus 5. One term, one thing with 2 terms, right? Give me a numerator that factors into something with x plus 5.
X plus 6.
Give me the whole thing, though.
X
You
squared plus 6x plus 5.
yeah, the easiest one, right? Just take 5 and 1. That's how you make your own problems, right? You want to make one with a hole, well, there you go. It's got a hole, because you know what the factors are. So start, as we said, by factoring this. All right? Now, right away, we're going to cancel certain parts. Cancel, cancel. That means at x equals -5, we have a hole. How do I find the y value? It's not a value because it doesn't really exist, but the height of the hole. Call it the height. Okay, the height of the hole is the word we use for this. How do I find the height of the hole? Kate, what do I do?
Plus -5 towards the one remaining x.
Very good. Evaluate the simplified function, which is really just x plus 1, with -5. So -5 plus 1 is -4. So the hole is here. of these in your homework, and you're like, really? This is interesting. You should be able to know what this looks like instantaneously. Look at the simplified form. What is it? What's the simplified form? A linear function. Remember, the simplified form gives us the actual function for these parts when the whole exists. When there's not a whole, if this numerator had factored into x plus 1, x plus 3, then we had a vertical asymptote, this would not look like a linear function. But whenever there's a whole and you reduce it, you can look at the simplified form to see what the function would look like. Write that down. No, Kate was the only one that answered that. As soon as you have a cancellation with a whole, you can look at the simplified form to see what the function should look like. And this answer is easy now. It's just whatever's left, x plus 1. So I could even really kind of stop here if I wanted to and not do the rest. Because if you do a slant asymptote, what are you going to get? Right? This would be slant asymptote, agreed? When the numerator has a higher degree. Do the slant asymptote. What do you get? It's just x plus 1. The same thing as what you get because you're dividing. Isn't doing the slant asymptote using synthetic long division? So you're really just dividing. Isn't that what we did when we canceled x plus 5? So if you do a slant asymptote right now, you will get the simplified form. So as a result, x plus 1 is really just this. But where's the whole? The whole is back here at negative 5, negative 4. That's it. That's the whole function. The whole function. So when you have a whole in a graph, please look at the simplified form, and if you can graph that, you're done. Okay, you're done. Now, to make it a little trickier, you should practice something like this. Let's go to the slide, actually. You should practice something like this. Go to Wolfram, put the numerator into Wolfram. Okay, if you put the numerator into Wolfram, you'll get an expanded form. Then practice getting the factors and go through this process, because you'll probably have something like this. Now, if I had this problem, what cancels right away? So what kind of a function will this one look like? Just look at it now. What's left? It's a quadratic. So if I were to graph this already, I know that it's going to be a quadratic. And believe it or not, if you tried to find an asymptote, it would be a quadratic asymptote instead of a slant. And the quadratic itself is the asymptote in this case. It happens to be the asymptote. So at negative 2 would be one of the roots, and at negative 1 would be the other root. And this would open up, and the y-intercept would be 2 times negative 3. Let's just do 2 times 1, actually. This is 2. Y-intercept is 2. So it means that there's symmetry on this side, which means that there must be a minimum somewhere down here. Now, where's the whole going to be? At negative 3. So if I recall, this is negative 1, this is negative 2. The whole is going to be over here. Actually, the whole will be right here. The whole will be symmetric with the actual y-intercept. Because this is... Sorry, the whole will be on the other side. I apologize. Thank you, Luke. Good call, Luke. The whole would be on positive 3. So all the way over here somewhere. Okay, that was where the whole would be, all the way up there somewhere. Yeah, good point, Luke. So again, this weekend you have 3 things to practice. Test 12 review, then there's a bunch of examples already solved. You can review them yourself. It looks like a PowerPoint almost. And then there's a third thing on business applications. Maybe something on the test plan. So apply this. Okay? So please take a look at documents and handouts. Look at all 3 of those documents over the weekend.